Okay, I guess it's recording now. Yes. Okay. So welcome to this first lecture on acoustics. It is about some fundamentals, terms in the physics of sound, just to make you familiar with some basic principles. And maybe it's very easy, but still we say, what is sound? I familiarize you with the acoustic units. I still find it very interesting to see the human ear and how we, or evolution, made sure that we can hear. And this is like a role model also for microsystems technologies, while nobody tries to imitate the ear in all its aspects, but it is still interesting since it is so major and so high in quality. Some fundamental equations about sound and sound phenomena, leading us to simply reflect wave phenomena, whether they are relevant to microsystems technology or not. And always I sum a little bit up. So, sound. Basically, we can say is vibration transport of energy via solid states or liquids or gaseous media. So in this lecture, I will concentrate on gaseous media. This is a difference, but we have to reflect what it means also sound in solid states or liquids. So, and then if we say sound is connected with pressure changes, we are at normal pressure 10 to the 5 Pascal. It's a very high total pressure, so to say, but we are used to it, of course. And if this pressure is not changing, of course, over time, then there is no sound, it's silence, we can call this. And any change or variation of pressure over time is sound in air. And what does this mean? Sound is anything for sure. This is noise, something. And how much is the level of the sound pressure level that we envisage? This may be the basic question that we are dealing with here. And sound propagation, we know, and I have here a simple example. Now it's closed again. I can open this hopefully. Yeah. It's just a simple particulate model, and we see that we have a propagating wave. We have a longitudinal transport of mechanical energy, so to say. This could be a solid state, a rod, a gaseous environment, or whatsoever. But the transport is by particulate interaction in longitudinal direction. And the wavefront is perpendicular to this. Very simple. And what we see, we have particulates that move with respect to their rest position. And this gives negative and positive pressure changes with respect to the ambient pressure. So this is a little page where you have some examples of modeling on acoustic phenomena. Very simple this way, yeah. And if we look into the molecular area, what happens in air, it is also quite interesting to relate to this. So basically, if you have normal pressure and a volume of air, we have Brownian motion in a cube, so to say. On particle level, that means that we have particles some sub-nanometer diameter, while the diameter of the atoms in a gas is interaction diameter. So what does this mean? Is this the size of the molecule in sense of interaction in sound, so to say, yeah? And then those are 3 nanometers apart from each other in average, so 10 times the distance between the number of particulates, just to say it like this. So we have only 0.1% of occupied space. That tells us already that if the atoms interact with each other, like a traveling wave, there's so much empty space. So the coupling in the gas is, of course, very weak. And so this has to do with transportation of sound waves. But the free mean path of collisions is already 60 nanometers. So while the average distance is small, until molecules hit each other, by instance, depends on the space, and this gives the free mean path between collisions, 60 nanometers. So some people call it quasi-vacuum if you have distances of plates or of dimensions in the micro or nano technology that are below those 60 nanometers, because then eventually you don't have collision between molecules, and this is already a hint about the limitations of classical physics of gases. And then the speed is something like 500 meters per second, is incredible. And if you later talk about speed of sound, has nothing to do with the motion and the rapid motion of those molecules. And with this high sound and this wide mean free path between collisions, you still have 10 to the 9 collisions per second. So these collisions give you kind of an inner energy of your systems. We call this Brownian motion or inner pressure of the system. And this is just the situation. If you now start to quench this volume or reduce this, press this together, and you do this slowly, then you have an isothermal situation. That means you compress your volume, you generate a pressure to the volume, and then the pressure change is directly proportional to the volume change, and there's a constant in between. Yeah, but the heat that you generate by compressing your volume will be dissipated to the walls. And yeah, there's no wonder you can do so, and it's just a fact. And you can calculate this by ideal gas law. Now, if we go to sound, we have the situation that we do fast changes of volume. So maybe as fast that there's no heat exchange with the wall anymore, because we do it with kilohertz or so. And then you don't dissipate the inner energy when you compress your device. In the adiabatic case, you have a higher pressure development. And the additional factor is the adiabatic ratio of specific heat for air in this case. This factor is a 1.4. There's also a reason for this. Diatomic gas is O2 or NO2, N2 or whatsoever we have in air. So 40% higher pressure development in adiabatic systems. This is just simple facts, and there's reasons that you will find in microphones very late in the lecture that we have to respect adiabatic or isothermal effects. And yeah, I have to shift this bar. So it is interesting or important to note that if you talk about acoustics, then we have small pressure fluctuations or low velocities. Speed of sound is small typically. So this is important in understanding what we're doing. If we had very large pressure changes, we could not simplify our description of sound. So basically we have this adiabatic system, the pressure change over generates a volume change or vice versa. And adiabatic state equation for gases is then the relative change of pressure is equal to the relative change of densities with the exponent of kappa, and kappa being the ratio of the specific heat of gas at constant pressure versus constant volume. So these heat capacitances are different by a factor of 40% for air, for example. And then since we say, yeah, we want to linearize this equation, we say we have little pressure changes. So the green pressure here is a small deviation from the reference pressure, 10 to the 5 bar Pascal, for example, and this may be only 1 Pascal. So we can count this as small. Then the same is true for the density, and then we can develop this equation into finally it is 1 plus kappa times the ratio of density. So if you have this Finally, the change in pressure is proportional to this equation, and then we can simplify the equation. And then it's interesting to compare pressure and density, because pressure and density are always connected with speed of sound by square. And this is giving us the definition of this sound velocity or speed of sound. And we see from this equation that speed of sound is proportional finally to the square root of kappa times the pressure to density of air, the reference pressure densities. And of course, we know from the ideal gas law that they are related just by the numbers of Reynolds number and the molar weight of the molecules in the gas. So finally, we get here the relation of the speed of sound, which is material constants, gas constant, and the total temperature of the gas. So finally, it tells us that the speed of sound is basically proportional to the root square of temperature. And this is also important to note. And I can share this on the next slide, that speed of sound depends only on the total temperature and maybe the composition of gas, of course, and if you have humidity in the gas or more CO2, this is true, but then finally only the temperature. And I have here a graph of speed of sound over temperature. Basically, it changes by 0.6 meters per each degree Celsius at about room temperature. So this you can keep in mind very easily. But in total, we have something like 340 meters per second speed of sound. And why is this? I focus on this because a lot of people tell me or have in mind that the speed of sound depends on the pressure. And this is not true. But it comes somehow in the discussion that speed of sound changes with altitude that you are living in. This is not true. With the altitude, of course, the pressure is declining if you have climate or if you climb a hill or so. But typically the temperature is dropping with altitude, especially in higher atmospheres. And it is finally only the total temperature which makes the effect on the speed of sound. So, of course, the hotter it is, the higher the speed of sound is. And if it is getting cold in the air, the speed of sound drowns, same as the pressure drowns, but this is just an coincidence. Good, yeah. And let's a little bit compare speed of sound for different media. Everybody knows speed of sound in air is low, 340 meters at roundabout. And yes, we can compare always the bulk elastic modulus, which is tiny in air, 0.14 megapascal. This is like nothing. And as a modulus for people who are going into the MEMS arena, they have modulus of solid states in mind. There's nothing. And again, related with the loose coupling of energy transport in this medium. And of course, density is also small. That makes a low velocity in air. If you look into liquids like water, modulus is much higher. It is nearly incompressible as well. Density is high, so we get an order of magnitude higher speed of sound, and nearly another order of magnitude higher speed of sound in solid states because of the tight coupling and the high weight. So this is a fact, and for sure this also is reflected in the physics of transportation of sound. We know we want to detect airborne sound with solid states, and this should tell us something, and is basically also the issue that we have to solve in here. Yeah, some simple acoustic units. Yeah, we had this picture, pressure coupling in longitudinal way, transversal wavefront. I said already, particle is the delta with V as a particulate velocity. This is not the speed of sound, finally. And yeah, simple definitions of amplitude and wavelengths. As usual, I don't have to talk about this. So we have a sound density, not very often used, but we mean only the AC portion of the change of density if we talk about sound density. Usually we talk about sound pressure. This is the same. So we are talking only about the RMS, or the change of pressure over the total pressure, or with velocity the same. And then there's a unit that is called flux. Sound flux is a little bit unusual, this dimension or this idea. So Q is velocity times the area the wave passes through, or the velocity passes through. So this comes in meters cubed per second. A bit unusual, but sound intensity is something like the pressure that mitigates with the velocity. And finally, we can press it in watts per meter square. So typically the units in the acoustic domain are a little bit different than those in other domains. So we deal a lot with volumes, and then finally we will see meters to the fifth and something like this. And we have to be always careful with the units and the expressions. Sound power is not so much used. It's basically the power of a wave integrated over an area, intensity integrated over the area. So going back to the pressure, sound pressure, and we define a sound pressure level, or not we, but this was defined by Alexander Graham Bell, and the name Bell comes to the decibel. Deci is the Greek for decade, so a factor of 10 or tens. So we need a unit or a simplification. How is this done? Basically, as I said, we're talking only about the fluctuations of total pressure, or the root mean square of those fluctuations. Take this in mind, that never mix up amplitude of sound pressure and the RMS. If we talk about sound pressure levels, is an RMS value. And since sound pressure or pressures vary from 10 to the 5 to micropascal, it is necessary not to work with orders of magnitude, but we do the logarithm. So basically, we divide the measured RMS pressure by a reference pressure, take the decadic logarithm, and multiply by 20. This gives the SPL, the sound pressure level. And that makes decibel. Everybody has heard the decibels. Where comes the reference pressure? Reference is 20 micropascal. So 20 micropascal is basically the theoretical or the best limit of human hearing. If you have this 20 micropascal and you have very good ears, and you have this pressure at maybe 1 to 2 kilopascal, you might be able to hear this. And this is then 0 decibel. So 0 decibel sound pressure level is the limit of human hearing, so to say. And then 1 decibel is a tenth plus. And the question is, yeah, working with decibels is at the beginning very unusual. For example, a factor of 2 is equivalent to plus 6 dB in sound pressure level. And sometimes you find this on your hi-fi devices that give plus 6 dB is just double sound, and this is where it is coming for. Or a 10-fold sound pressure level is plus 20 dB, and so on and so forth. So you see, instead of large numbers, we have now additive numbers to work with, and this is much easier. Okay, just to give you an impression about the scales. As I said already, we are at ambient pressure 10 to the 5 Pascal plus minus 300 Pascal. 300 Pascal is maybe weather phenomena. and 10 to the minus 5 is the limit of hearing. So it's 10 orders of magnitude already that we cover here. And you have here the what physicists typically do. They do exponential scale on the left-hand side. The engineering scale is with decibels. And just to see what we have in here, if it is a very calm breathing in night in a quiet room, maybe you have something like 10 decibels. Typically, a quiet room is something like 30 dB. 40 dB was in the past telephones. So if you have quiet environment, you can hear this noise. Conversation, 50 to 60 decibels. Passenger cars are specified for 70 dBs typically. The road is getting already bad, so you have something like 84 decibels if you're 10 meters away from the road. Something. If you have this at work, this is starting where you have to wear this ear protection for work environments. Then 1 Pascal, this is typically the level where we specify sensitivities of microphones or whatsoever, is 94 dB SPL. So you keep the 94 dB SPL as a reference point in your mind as well. And it's going higher and higher and higher with jet engines, 150 dB. At least at 120, 130 dB, you get ear issues in short time. And somewhere there's also a limit where you get dissociation of air, some below 200 pascals. It's still not a very high pressure. It's not even 2 times the ambient pressure here. But if you have sound with these levels, it's the limit that you can transport with air, then it's not working. The question is, how quiet can something be? So I know that the Brownian motion of particulate in space, so there's nearly no particulate, but then still there is some. Theoretically, this is minus 23 dB sound pressure level. It's a factor of 100 below what we typically do. And for this, people are developing anechoic chambers to have quiet environment for testing of good microphones, stuff like this, and research. I have just a nice video here, if this opens up, displaying how quiet a room can be. I display this with you. I don't know whether there's the world record about the most quiet room. No, come on, where can I start this? An anechoic chamber. Yeah, and they try to do a world record for the most quiet room and still not broken this record.
This is the anechoic chamber. One thing to notice are these wedges. These are sound absorbing material. They are anechoic. That means no echoes. All the sounds are absorbed. To give you a rough idea, the Brownian motion, that is a random air particle in space, is around minus 23 dB. You can't get any quieter because that's just the air particles moving. We are at the edge of what is the limits of physics in that sense. We have exercised attention to every detail as much as we can. For any measurement we do in engineering and science, our criteria is to say, is it a meaningful measurement? And that just means, is it valid what you're doing? It has to be repeatable. To do that, we need highly controlled environment. So these labs are about creating rock solid, acoustically controlled environment. When you plug in your power supply into your device, for example, it makes noise. when you adjust the brightness of the display on the screen, it makes noise. This chamber gives us the opportunity to look for those really small signals that can have a big impact to the end user. One of the big things right now is personal assistant, right? Like Cortana, for example. I think you'll see more and more that Cortana is becoming a bigger part of your life in general. For that to work well, audio is very, very important. Audio on the microphone side and audio on the speaker side.
I'm sure there are a lot of people trying to do that, right?
Yes. Yes.
So we want the
Yes.
bar, yeah.
We always want to have the best tools available for the job. This is what it is. It's the best tool available. I think within Microsoft, it's a tool that we can use across the company for scenarios we probably haven't even thought about yet. It'll take a huge effort. If it could have been done, everybody else would have been doing it. Guinness tells us we need to reach minus 13. I think we're going to get to minus 16. I think we're going to beat it by 3 dB.
Let's record it and let's pause process the data.
For 3 minutes, approximately. Go for it.
Let's analyze that. Okay, we're going to push that to the templates. Okay, 20.6 dBA.
That beats the world record. I think we did it.
So I stop here. It's just the explanation how quiet rooms can be. Stop it. And you see this anechoic chamber, quite huge. It's not really a mechanical reference point in here. People are walking on net instead on floor. If you are in such a room, it's quite spooky. You only hear your body voice and not the reflection of the environment around. So it's really anechoic, and you cannot work for a long time in such a room. I've been working something alike, but you are happy if you get out again. It's a little bit special. So very tiny sound pressure levels, and you see how much effort they do, and all this audio equipment for referencing and testing always underlies the noise limitations, and we will discuss this as well. The self noise of the device limits the capability of record small signals, and this is the most important parameter in such a microphone, for example. So yeah, we were discussing this already. Okay, if you're talking about sound pressure or sound velocity, and we do the sound pressure level calculating from there, then 2 times the sound pressure level is plus 6 dB. If you go about power or intensity, then it is 2 times the power, which makes plus 3 dB in sound pressure level. So this is simply the relation between power and pressure, where's a square relation in between. But typically we go for this. Now again, we go back to understanding a little bit the human ear. I bring a little bit insight into the physiognomy of the ear and the hearing. So if you look at the audio band that we are typically referring to, it is between 20 Hertz and 20 kilohertz. Below we have infrasound, and this is even sometimes related to body noise or conduction. Beyond we have ultrasound, and there's even hypersound. Hypersound typically does not take place in air and gases anymore, but you can do this typically only in liquid or solid state. Typically this is something like the medical detections. So all the animals and people on Earth that are living in air I check whether there's even fishes in. No, I don't see. Beluga whale. Okay, beluga whale in liquid goes up to the ultrasonic. Sure, who is in water can take advantage of the higher speed of sound, and then ultrasonic is more a good way to communicate. But we see that nearly everything is in this 20 kilohertz bandwidth. Yes, okay. And so we study this basically. If we see how the reception of human ear is, we don't have sensors like physical devices, but we are having a special reception only, which is not flat, but we have a hearing perception which is bad at low frequencies and is good at higher frequency, and is best around, let's say, 2 to 3, 4 kilohertz typically. And for this, we have these phone lines. Phone is the unit for hearing reception, typically defined at 1 kilohertz. Or at 1 kilohertz, it is identical to sound pressure level. But you see here that basically at 20 hertz you need 40, 60, 50 dB more sound pressure level to get the same hearing impression or same loudness, so to say, as at 1 kilohertz, and at high frequency a little less. So this is just a fact, and is also reflected with the fact that it is matching to our speech, of course. So if we have high frequencies like S tones and so on, not vowels, they are sharp, and they are very important to understand language and the fine details of language. There we need more sensitivity to distinguish between the different words and stuff like this, while the vowels, O, E, I, is easier to distinguish. You don't need so much energy to understand this. This also finally deals with speech recognition systems, why they need high sensitivity at high frequencies and wide bandwidths. There's a lot of reasons to deal with this. Finally, yeah, this matches, of course, yeah, good, and is no wonder, because nature has done it this way. And yeah, we reflect this typically when we define sensors that have equal response over frequency, because in engineering we can do this easier. Then we weight the frequency response with some filter function, and the A filter function is the inverse of our hearing perception. So it weights low frequency less, is the blue curve, and higher frequency a little bit higher. And if we rate the signal to noise ratio of a typical microphone, we ask, is it filtered, A filtered or not A filtered, because we want to have the A filtering to be able to compare this with the impression that we have as humans. While if we have technical applications like machine conditioning, we don't need this comparison to the hearing perception. Yeah, so this is a cross-section to a human ear. A fundamental question, can we learn from there to generate the best microphone, for example? The ear is complex, and for sure you have seen this in school or before. Outer ear until the eardrum is here, then the middle ear where we have the bone conduction, and the inner ear where you have the connection to the nerves. Now let's go a little bit into this. Interesting is already the ear channel, which has a dimension of 2.5 centimeters, a volume of 2.5 centimeters cube, cross-section of 0.4 centimeters square. If you have such a channel, such a tube, you find out that there's a resonance between 2 and 4 kilohertz somehow. And this is the resonance, which is also important to our high frequency understanding. The S and what we saw in the perception of the human ear is accelerated or supported by the resonance of the ear. We're not talking about the outer ear. This is also doing with a lot of features for hearing, but only this ear channel is already a good hint why we hear better and how we hear better with a resonator in front of our eardrum. Then again, we have the volume of the middle ear is also giving kind of a resonance in this area. So it is supporting, it's like also kind of a resonant amplifying system in this frequency range. So takeaway is there's a transducer that is transducing from the sound field into a sound coupler with a resonance into a mechanical device. The mechanical transduction finally is an energy domain into the fluidics, because the inner ear is a fluidic device. And finally, again, from fluidics on mechanics, and the mechanics into electrical signals, which is stimulating the nerve. So many transduction principles in one organ. And why is this? There must be a reason. It must be the optimum, so to say. For sure, I don't want to repeat this in a MEMS systems, but somehow we do so, and we will learn how. Yeah, there's just another representation here. Again, there's 3 bones that are doing the job. The 3 bones is something like a lever system. So with the first malleus into the incus and to the staples, which is going to the inner ear, connected to the drum of the ear. So it's incredible, and if for a mechanist, this is for sure something he can do. We see somehow that over this pivot, we have an amplification, just a lever system. And coming from the sound coupling to a diaphragm and this into mechanics. So this effect only, this mechanical transformer, helps us to reduce the reflection of sound to the mechanics from 98% down to 40% reflections. So then we get better connection to the energy from outside, and it's just by those bones. This is finally a factor of 22 or plus 13 dB, only mechanical amplification. Yeah, this is something we always keep in mind if we go for other systems. The second transducer is then if you have the mechanics, and this is the staples here, working on the inner ear. The inner ear is this basilar membrane. We can have a look at this video as well. It's maybe easier to understand. I hope the internet is better now. Oh, goodness.
You're looking at an uncoiled cochlea containing a basilar membrane floating in endolymph. The organ of Corti, which contains the auditory receptors, sits upon the basilar membrane. Movement of the basilar membrane stimulates the auditory receptors. Notice 2 structural properties that determine the way the basilar membrane responds to sound. First, the basilar membrane is wider at the apex than at the base by a factor of about 5. Second, the membrane's stiffness decreases from base to apex, the base being about 100 times stiffer. When a sound wave pushes the footplate of the stapes at the oval window, endolymph is displaced within the scala media, the chamber containing the basilar membrane. Movement of the endolymph makes the basilar membrane bend near its base, starting a wave that propagates toward the apex. The distance the wave travels depends on its frequency. This high-frequency wave vibrates the stiff base of the membrane a good deal, but most of the energy is dissipated before the wave propagates very far. Now, notice the difference in the traveling wave generated by a low-frequency sound. This generates a wave that travels all the way up to the floppy apex of the membrane before the energy is dissipated. These vibrations in the different parts of the basilar membrane establish a place code for sound frequency. This is because different locations on the membrane are maximally deformed at different frequencies. This mechanism is responsible for neural encoding of pitch.
Yeah, this is quite simple. So we have the high frequencies at the beginning of this basilar membrane and the low frequency at the end. You see here spatially the different resonance frequencies that you develop.
All right, Ninja Nerds, in this video, we are going to talk about the cochlea. So if you guys haven't already, please go and watch our video on the anatomy of the inner ear. The reason why is we said in that video that we're going to dissect the different.
Sorry, what's strange going on. So then spatially, we have different frequency at different places. And this is mechanically quite nice because then I only have to detect the actuation at different places. And this is finally the reason or the way the nerves are doing. The nerves are not frequency sensitive, but only switches, like digital pickup, so to say. And as these nerve cells are connected to the membrane between the two liquid chambers and getting into resonance, resonance will only modulate the switching of those nerve currents into the cells and then giving this simple signal as reflected to one frequency. And yeah, this is simply, you could model this as an electrical switch. So I put this once again in this very simple mechanical transducer. So we have the front ear, the drum, the mechanical lever into the liquid. And this is the basilar membrane resonant, but the fluid, keep this again, this in one direction it vibrates and is connected to the lower one and is equalizing the pressure, but it gives this kind of a traveling wave phenomena, which is finally on this diaphragm. So this is a simple mechanical representation of the ear. This is the electrical equivalent description or a lumped model where you see we are using pressure into flow into the ear, and then we have an energy transformer transforming it into a volume pressure into the middle ear, and this is again transformed into the cochlea, and finally in the cochlea you do a simple kind of transduction model, an electrical model. So we know we have something like 8 millivolts working on those nerves. And you see here, we end up with an electrical stimulus. And this is not so much different from what we will do with the microphones. We go with a sound pressure input, and we end up with an electrical stimulus. And we go via different domains this way. And this we will learn for microphones. And a MEMS engineer gets a lot of ideas how we could replicate this. We still have to keep in mind that our ears are very expensive, and if you have a hearing disease, you will find out how expensive this is in medical aids. A microphone for some consumer application has to be very, very cheap. For this, we cannot do all those transduction programs. We have to be more simple. Okay, this was a little introduction into the human ear. Now we come to some basics, the basics of fundamental hydrodynamics. We start on the very top level with the Euler equation. This is the way to formulate movements or changes or transport in compressible fluids like gases or liquids. And we take always two equations, the movement and the continuity equation, to describe whatever in the medium is going on with dynamics. So the movement is like the simple force, which is balanced, an external force, which is balanced by the movement of inertia, so the total rate of velocity over time, and the gradient of pressure, of course, yeah, if you have a total gradient of pressure, which is in audio effects typically not the case. And on this other side, we have the continuity of mass or mass conservation. where we have changes of density over time, equalizing or balancing the volume flow, which is described by this term. So this is the two fundamental equations. And from there, we should be able to finally derive wave phenomena and acoustic descriptions. Now, if we move on here, we see that we have in the formulation the total derivative rate of velocity over time, which causes a lot of trouble in this movement formulation. Because if you start developing the total derivative rate over time, we get a partial derivative and this velocity times grad of velocity. Then we can develop this further, and this gets a gradient of the squared of the velocity, and it gets a rotation in the formulation. So this is then the developed Euler equation, and it starts to get quite complex. For sure, this is highly nonlinear, extremely difficult to solve, and the question, can we do easier? Yes, we can. With this, if we found solutions in special points, we not even would be able to superimpose them to generate a solution because it's so nonlinear. So this is only the fundamental description. So we need a simpler way of doing so. And yeah, we do simplifications. And one simplification, for example, is that we do eddy-free fluidics. So we are talking about small levels and eddy-free to simplify, because this is typically the case in communication. If we had eddy flows in communication, I'm sure we couldn't communicate anymore. I don't know how to express this, but we are in very small signals and homogeneous fields typically. Then we can develop the velocity or the pressure in the total pressure and a small deviation, and the small deviation is finally what matters. And finally, we end up that we only have to respect the partial derivation of velocity or pressure. And then we get a way that we can simplify for the Euler 1 and the Euler 2 is unchanged in this perspective. And with this, we can proceed then simply. Important to keep this in mind. For example, if you later on might go to ultrasonics or to limitations that are not respected with this equation, then you maybe have to go back to the Euler equation. I'm sorry for that. So we simply rephrase this Euler equation for force-free situation, because force-free is the situation of a traveling of a homogeneous sound field, so to say, propagating wave. So then we can reformulate this, and we also have the velocity of sound defined here, and this gives then partial this equation that we again derive over time. And if we do so, we get basically a wave equation, which is a wave equation only in pressure. This we could solve as a typical wave expression. We can write this wave equation in density or velocity or even in potential, while we are used to do this in pressure. Okay, this is standard and is valid for other wave phenomena for small deviations as well. So if we prove this and we take a traveling wave in direction x, we simply do this amplitude times the cosine of a wave. We can put this in our wave equation. We derive it respectively and get finally the velocity with the second derivative. And what we find in here, no wonder, is that the velocity wave is in phase, again a cosine, such as the pressure. So we learn from there that pressure and velocity are always in phase in a typical traveling wave in one dimension. And if we have this situation, we can define an impedance, a characteristic impedance of sound, which is the ratio of the pressure amplitude and the velocity amplitude, or the two waves. It is again ρ0, or density times the velocity of sound, and this is Z0. This is the characteristic impedance of sound. And of course, we as engineers like to work in impedances. Then we can just about energy transfer and all kind of wave phenomena. For this, we define this characteristic impedance. And again, I try to show what is the effect of impedance and how is impedance looking like. Just to see here, we have the characteristic impedance of air, 410 kilogram per meter square and second, or you see here Newton seconds per meters cube. It's kind of an acoustic units. We do the same impedance, characteristic impedance for a liquid. It is 3 orders of magnitude higher. And then we go to solid states, is 10 to the 6 20 times. So it's again a factor of 10 higher, so to say. So we have nearly 4 orders of magnitude higher impedance from gas to solid state. And our microphone will be a solid state. And if we have this, we have an impedance issue. And this is so important to say. And keeping this in mind, we check some wave phenomena quickly. And the first wave phenomenon is reflection. So a reflection coefficient can always be expressed as the impedance of the media and the impedance the difference of the impedance of the two media. So if you have Z0 being the acoustic impedance of air and Z the acoustic impedance of the wall that we are hitting at our sound, or this is maybe the membrane of a microphone, so to say, and we say we don't have absorption. If we go from air to water, we have 99.9% of reflection. Air to silicon, which is our material of choice, it is, I could say, 100% of reflection, or in decibels is minus 88 dB. So this is like a hard wall with a nearly perfect reflection. And with this situation, how could I pick up sound from a sound field, which is anyhow tiny, with a few pascals or millipascals also only, and then I have a reflection coefficient so hard. So we need to get our sensor soft somehow to take the sensitivity or to match the impedance of air. And we have seen that the ear is doing something with a soft diaphragm and then a mechanical transduction, and is still reflecting more than 60%. This is basically a big job to solve for microphone application, and vice versa. If you want to have a speaker, the situation is similar but inverted. Yeah. Everything else like reflection law, refraction, this is more or less always the same. So it's not a big difference to optics. You can calculate the same laws. Also diffraction happens. So there's the principle of Huygens that you can add up point source to get field situations. There's only the typical dimensions interesting in here. So if you say we have 1 kilohertz tone, the wavelength is 34 centimeters, big bunch, yeah. And there's 2 simulations. There's an aperture of a homogeneous sound field, which is hitting a wall and then emitting through this aperture of 17 centimeters. And then you get this typical diffraction pattern behind this big hole. It is still like a point source. And only if you have a door opening of maybe 170 centimeters, as in this reflection, you see that you get a homogeneous wave traveling with those typical interferent or diffraction pattern. Also, you see here the reflection from the edges and so on. It tells us already that everything is bigger in acoustics than typical microstructures. And for this, basically with the microstructures, typically we are in a homogeneous pressure field and not find so much wave phenomena. Yeah, there's just, we saw also in the video of the anechoic chamber, they're using these kind of reference microphones. These are typical reference microphones of 12 millimeter diameter, which is very high quality, very high level, and expensive, by the way. So you start to see wave phenomena in here, while you have a homogeneous field approaching this front plate of the microphone. Eventually, you get a little bit compressed air in front, so to say. Yeah, you get diffraction at the edge of the microphone. So all in all, it yields up a little bit higher sound pressure level if the wave comes directly from the front side. You find this is coming 10 kilohertz and above, significant. So there's some 60 dB of higher sound pressure level just due to the fact that the microphone is disturbing the sound field. And if you revert the microphone by 180 degrees, you have a little less sound pressure level. This is somehow intuitive, but you see that only at high frequency and quite large dimensions, such phenomena come in play. And these are the limitations then where you start thinking about wave phenomena. But if you do microphones like millimeter size dimensions and micrometer size dimensions, for sure, you don't get into conflict with those typical dimensions. Yeah, this is just, again, this expressed in wavelengths. So we are between 20 hertz and 10 kilohertz. 20 hertz is already 20 meter or something in wavelengths, 30 meter in something huge wavelengths. I don't talk about wave phenomena, and 20 kilohertz is around 2 centimeters. People that are doing ultrasonic devices, CMATs, PMAT, whatsoever they are called, they start to see wave phenomena, and then you see array functionalities that are in the dimension of the wavelengths. But this is just to be respected. If I see publications that try to do wave channeling or tube systems to do impedance matching to sound speed, and they do it on the centimeter level for a microphone, I have to tell them, you didn't think wise about audio and wave phenomena. Yeah, last but not least, quickly reflect what I teach to you today. Sound as longitudinal and particle movement. We can take away that the pressure is typically proportional to the acceleration of the particulates in the field of sound. This is important if we later on talk about speakers. The typical acoustical unit sound pressure level is 20 times the logarithm of the ratio of the RMS pressure by the reference pressure being the 20 micropascals, our limit of hearing. If you have 2 times sound pressure level, it is a plus of 6 dB. Yeah, what you take away from the human ear, very elegant solution of physical domain matching with impedance transformation. Somehow it does it well. And from the Euler equations, we finally find the chance of the speed of sound, which is proportional to the temperature. And this is always for loss-free and linear systems. And wave phenomena gives us the impedance of sound, 340, now 410. Oh, I forgot the unit. Newton seconds per meters cubed, sorry. Now I have it, yeah. This is something which we take away, and MEMS structures. Yeah, I'm happy that we don't talk too much about wave phenomena. Then it is easier compared to optics in the microsystems technologies. We are talking about pressures and pressure fields. Okay, with this, I would stop the lecture, and we didn't have questions in between.